A hint at the answer. Operation Desert Storm of February 1991 provided a fascinating example of modern U.S. versus Soviet-built tanks in action. This conflict was not a perfect surrogate for a NATO-Warsaw Pact clash, since the latter had better tanks than the Iraqi T-72M1, and Warsaw Pact crews were probably better than the average Iraqi tank crews. Nevertheless, close examination of these tank battles provides an intriguing look at the state of tank technology and tank warfare at the end of the Cold War. Desert Storm was not the first war which pitted U.S. against Soviet equipment. The first significant clash occurred in Korea in 1950 when the North Korean Army spearheaded their attack on South Korea using Soviet-supplied T-34-85 tanks, and the U.S.-led intervention involved M4A3E8, M26 and M46 tanks. Although the North Korean T-34-85 tanks proved to be highly effective in the initial invasion when faced with poorly trained South Korean infantry, once they were challenged by U.S. Army tanks they suffered massive losses. The reasons were far less to do with the technology of the opposing tank types, which was fairly similar, but instead it was primarily crew quality which made the difference. The U.S. crews were better trained than their North Korean opponents, and this core issue of crew competence would resonate through many later Cold War tank battles. The 1956 war between Israel and Egypt involved tank combat between U.S.-built Sherman tanks and Czechoslovak-supplied T-34-85 tanks, and once again the results were heavily dependent on crew quality. The 1967 Six-Day War saw the first major clash involving tanks developed after World War II. The Israel tank units largely relied on the British Centurion and US M48A2 Patton tanks, while the Egyptian and Syrian forces used Soviet T-54 and T-55 tanks. However, the tank battles were one-sided in favor of Israel even when Israeli units used modified Sherman tanks. And the importance of crew performance was demonstrated especially clearly when Israeli Sherman successfully confronted the modern Jordanian M47 and M48 tanks. The 1973 Arab-Israeli War saw yet another generation of Cold War tanks put to the test, in this case the US M60A1 and the new Soviet T-62. The results of this conflict were not as lopsided as some of the earlier wars, though ultimately, the Israeli tanks exacted a punishing kill ratio against their opponents. These wars could not provide an entirely accurate model for a potential NATO-Warsaw Pact tank confrontation due to differences in terrain, tactics, training and many other factors. But time after time, they suggested that the ultimate factor in deciding the outcome of tank combat was crew performance and not tank technology. The technical balance between NATO and Warsaw Pact tanks through most of the Cold War was close enough that it could not alone determine the outcome of tank fighting. This book will argue that the same was true about Operation Desert Storm, but it will also argue that Desert Storm provided an example where there was not only a clear advantage in crew quality on one side, but that there was a much greater technical disparity than was the case in most of the previous clashes. The American M1A1 Abrams, German Leopard 2, British Challenger, and Soviet T-72 and T-80 were the ultimate tank designs of the Cold War years, and still have not been replaced by a new generation of tanks. Indeed, there is some question whether they will be replaced in the foreseeable future, since they continue to be viable battlefield contenders so long as they are well maintained and regularly updated. In recent years the focus has instead been on the adoption of a new generation of 5. The T-72 became the standard license-produced Soviet tank in the 1980s in Poland, Czechoslovakia, India, and Yugoslavia. Iraq was not the only army to use the T-72 in the 1991 war. The Kuwaiti 35th Fatah Brigade operated the Yugoslav-built M84A version as part of the Joint Coalition Force Group. U.S. DoD, lightly armored wheeled vehicles that are more economical for peacekeeping operations rather than high-intensity combat. Several features distinguished the M1A1/T-72 generation from previous generations of tanks. In terms of firepower, these tanks represented the final switch to the use of APST, armor-piercing, fin-stabilized, discarding sabot, ammunition, simply termed sabot in the U.S. Army, for tank fighting. While APSTs had already been used by previous generations of tanks, heat, high-explosive anti-tank ammunition had remained the predominant type in NATO and Warsaw Pact use through the 1970s. APSTs began to attract serious attention due to its extensive use by Syrian and Egyptian T-62 tanks in the 1973 Arab-Israeli War. The final triumph of APSTs was due in part to advances in ammunition technology, but also to improvements in fire control systems that gave APSTs a level of accuracy. 6. The M1A1 Abrams tank represented the culmination of a number of technological trends in the 1960s and 1970s, which included the introduction of a new generation of digital electronics. This provided substantially better accuracy at long range, the ability to fire on the move, and significantly improved capabilities to see at night and through smoke and fog. GDLS, resembling that of rivals such as guided tank projectiles. Both the M1A1 Abrams and the T-72 relied on APSTs as their primary tank fighting ammunition at the time of Operation Desert Storm. The greatest disparity between the M1A1 Abrams and the T-72M1 was not in actual gun performance but rather in gunfire control. The Abrams used a far superior FLIR, forward-looking infrared, thermal imaging sight. M1A1 Abrams. In the 1970s, the U.S. Army tank force was based on the M60A1, with some of the older M48A3 patents still in service with National Guard units. Both tanks were evolutionary descendants of the M26 Pershing tank of 1945. An attempt to replace the patent series with the more radical T-95 design failed by 1959, as did the subsequent American-German MBT-70 program in the 1960s. Frustrated by cost overruns and poor performance, the U.S. Congress killed the remnants of the MBT-70 program in 1971 and instructed the Army to make another fresh start. In the meantime, the M60A1 soldiered on through evolutionary improvements as the M60A3, TTS, with important innovations including a laser rangefinder, thermal imaging night sight, and a new generation of ammunition. In contrast to previous tank development programs, which had relied on the U.S. Army's Tank Automotive Command to undertake most of the design work, the new XM1 program was competitively developed by U.S. industry. In 1972, General Motors and Chrysler received contracts to produce pilots of the XM1. The Army did not want a repeat of the situation with the overly complicated MBT-70, and the price per unit was capped at $500,000. By way of comparison, at the time a single M60A1 tank cost $339,000. Due to time constraints, the Army decided to stay with the existing 105mm gun instead of the more powerful German 120mm gun being developed for the Leopard 2, with provision for the 120mm weapon to be adopted at a later date. One of the main innovations in the M1 Abrams design was the incorporation of laminate armor. The U.S. Army had been studying various types of advanced armors since the 1950s. And in 1972 the British government agreed to share details of its breakthrough Burlington Special Armor, often referred to as Chobham armor, since it was developed by the Fighting Vehicle Research and Development Establishment at Chobham. The primary aim of laminate armor was to defeat shaped charge heat, high-explosive anti-tank warheads which had become a principal tank killer through their widespread use in anti-tank missiles as well as projectiles fired by tank guns. With conventional high-explosive warheads, the explosive energy is released in all directions. In contrast, a shaped charge warhead is built around a hollow metal cone, and when detonated, the explosive crushes the cone and forms it into a hypervelocity stream of metal particles which can penetrate a significant depth of armor. Experiments had shown that the penetration effect of shaped charge warheads could be weakened using laminates. As the hypervelocity stream penetrated the layers, it tended to break up or be diverted, lessening penetration. In the case of the M1, the protection objective was to shield the front of the tank against both the Soviet 115mm APST projectile and a US 5 inches, 127mm, heat warhead comparable to that used in Soviet anti-tank missiles. 11. The 2nd Armored Division at Fort Hood, Texas. was one of the first units equipped with the new M1 Abrams tank in 1982-83, including these examples from 3 to 67 armor. Author: the XM1 designs also began to explore other methods of protecting the crew besides the armor package. The primary cause of catastrophic tank loss in combat is the ignition of main gun ammunition propellant. Since World War II, tank designers had advocated transferring the ammunition to the floor of the tank where it was least likely to be hit, in order to minimize this hazard. However, this configuration does not guarantee that the ammunition will not be hit, since mine damage or ricocheting projectile fragments inside the tank can still set it on fire. Furthermore, the floor location makes it difficult for loaders to reach and handle the ammunition, especially in view of the growing weight and size of modern tank ammunition. The U.S. Army began to explore the idea of moving the ammunition into a bustle at the rear of the turret. The ammunition compartment would be separated from the fighting compartment by sliding blast doors, and only open for a short time when the loader extracted a round. Should the ammunition be set on fire, the blast doors would protect the crew long enough for the men to escape, and in many cases would slow or prevent the spread of a catastrophic fire into most of the tank. One of the most controversial features of the XM1 was its propulsion. In the 1960s, the Army had sponsored the development of a gas turbine tank engine, the AFCO-Lycoming AGT 1500, originally considered for the MBT-70, in place of more conventional diesel engines. The Army's enthusiasm for the gas turbine option stemmed from the revolutionary improvements in gas turbine propulsion in Army helicopters. A gas turbine is a form of jet engine, but with the power output through a transmission rather than a jet exhaust. Gas turbines were significantly smaller and lighter than contemporary piston engines of comparable power. In helicopters, their simplicity resulted in lower maintenance demands and greater reliability. However, some notable challenges did arise in adapting gas turbines to tanks. A major one was their voracious consumption of fuel and air. Unlike conventional piston engines, 32.2 feet, 9.81 meters, M1A1 side U12, which can be slowed to idle to conserve fuel when the tank is not moving, the gas turbine operates near peak power all the time, consuming fuel. In addition, the engine requires a substantial flow of air, a more significant problem in a land combat environment than in the case of helicopters, due to the presence of dust which can erode engine parts. In the end, Chrysler selected the more controversial turbine for its XM1 design, while General Motors stuck with an AVCR 1360 diesel. Although both engines were rated at 1,500 horsepower, the actual amount of power available from the turbine was greater, since only about 30 horsepower had to be diverted to engine cooling compared to about 160 horsepower for the diesel. Both tank designs were subjected to extensive modify the design to accommodate the AGT 1500, and both potential contractors were instructed to modify their turret design to accommodate the German 120mm gun. Chrysler's efforts at cost reduction paid off, and the full-scale engineering development contract was awarded to the firm in November 1976. Low-rate initial production was approved in May 1979, and the first production tank was delivered in February 1980. The new tank was named after General Creighton Abrams, who had commanded M4 Sherman tanks in World War II, had been Army Chief of Staff in the later years of the Vietnam War, and was an ardent advocate of the new tank. The new AFV was formally type classified as the M1 in February 1981, and full production was authorized with a procurement objective of 7,058 tanks. During the course of production, Chrysler's Defense Division was purchased by General Dynamics, becoming General Dynamics Land Systems, GDLS. By this time it was obvious that the 105mm gun would be inadequate to deal with the newer generation of Soviet tanks such as the T-64B and T-80B. The first M1E1 pilots with the 120mm gun were delivered in March 1981, These pilots incorporated a 14. The final version of the M1A1 to arrive in time for combat during Operation Desert Storm was the M1A1 Common Tank, developed to incorporate special marine requirements such as the wading trunks needed for amphibious landing operations. GDLS. No sooner had the M1 entered production than the Army decided to press ahead with the M256 120mm gun, a simplified copy of the German Rheinmetall weapon. Variety of other improvements, most notably an improved armor package. Details of the latter package remain confidential, but a Soviet report assessed the armor protection for the M1A1 against APSTs as equivalent to 600mm RHA, rolled homogeneous armor, compared to 470mm for the M1, and 700mm against heat compared to 650mm for the basic M1. These features, minus the 120mm gun, were incorporated into the M1 production line with the confusingly named IPM-1, Improved Performance M1. 894 of the latter were delivered between October 1984 and May 1986. The 120mm version of the Abrams was type classified as the M1A1 in August 1984, and the first production tanks were completed in August 1985. Priority for the new version went to U.S. Army Europe, USAR, which had begun receiving them in large numbers by 1988. During the late 1980s, development of laminate armor packages for the Abrams continued, including a configuration using depleted uranium, that is, metallic uranium consisting of isotopes that emit little or no radiation. The principal advantage of uranium is its weight and density, which is about double that of lead. Depleted uranium was employed in a third generation of armor on the M1A1, leading to a variant dubbed the M1A1HA, HA standing for heavy armor. Besides being incorporated into new production tanks, starting in October 1988, the heavy armor package could also be retrofitted to existing tanks. The M1A1 and M1A1HA were the principal types of Abrams used in the 1991 Gulf War. 15 M1A1 Abrams specifications. M1A1 Abrams, 2-70 armor. 1st Armored Division, Medina Ridge, Iraq, February 1991. General Crew 4 overall length, 32.2 feet hull length, 26 feet width, 12 feet height, to top of machine gun, 9.5 feet ground clearance, 1.6 feet track contact, 15 feet track width, 2.1 feet gunner's night vision, Hughes thermal imaging sight drivers day/night vision day periscope/image intensification night vision commanders day/night vision periscopes, optical elbow to gunner's primary sight fire protection automatic halon procurement cost $1,624,000, 1988, motive power engine :1, 500 horsepower AFCO Lycoming gas turbine fuel capacity, 505 gallons performance maximum road speed, 41 miles per hour fording capacity, 4 feet without kit, 7.5 feet with kit obstacle clearance capacity, 4 feet power to weight ratio, 23.1 horsepower/T ground pressure, 14.4 pounds per square inch armament main armament, 120 mm M256 smoothbore gun main gun rate of fire, 6 revolutions per minute main gun stabilization azimuth and turret, elevation and line of sight main gun elevation, -10 to +20 degrees secondary armament M247.62 mm coaxial machine gun anti-aircraft defense. 50 calories Browning heavy barrel. M247, 62 mm smoke dischargers grenade launcher. 2 M1 Ural. The dynamics of the T-72 program were fundamentally different to those of the M1 program, and it was arguably less successful. A primary focus of Soviet tank development since the mid-1950s had been the Alexander Morozov Design Bureau's development of a new generation tank at the tank plant at Kharkiv, now Kharkiv in the Ukraine. This bureau had been associated with the legendary T-34 design, and before Kharkiv was overrun by the Wehrmacht in 1941, the plant and associated design bureau were moved out of reach to Nizhny Tagil in the Urals. There, The Bureau was given responsibility for the next generation of Soviet tanks, the short-lived T-44 and the more successful T-54. The Morozov Bureau returned to Kharkiv in 1951 and began work on another new generation tank, a Bayekt 430. A small engineering team remained behind at the Uralvagon plant in Nizhny Tagil to manage further evolution of the T-54 tank, starting with the T-55. This latter kernel would in the 1950s grow into a separate tank design bureau, headed by Elen Kartsev, which would begin to rival the original Kharkiv Bureau. Morozov's dream was to repeat the success of the T-34 with a revolutionary new tank that would match NATO tanks in firepower, armored protection, and mobility while remaining significantly lighter and more economical. The latest design went into production on a small scale in October 1963, as the T-64 tank. The T-64 incorporated a host of novel features including laminate armor in its glassy plate and an autoloader for its main gun. However, the design was plagued by problems, especially the poor reliability of its opposed piston diesel engine. While Morozov was trying to cure the problems with the T-64, Kartsev's Uralvagon Bureau had stretched the T-55 to accommodate a 115 mm gun like that on the T-64. The resulting T-62 tank, while not offering the armored protection or sophistication of the T-64, was much more economical to build and much more dependable. As a result of the continuing tribulations of the T-64, the simpler and less expensive T-62 became the more widely manufactured tank of the 1960s. Morozov continued to work on solving the problems with the T-64's powerplant as well as improving its combat performance by incorporating a more powerful 125 mm gun. The improved T-64 went into production in May 1968 as the T-64A. However, while reliability had improved over the dismal T-64, the mean time between engine failures was still only about 300 hours. The Soviet Army had hoped to standardize on the T-64A as its new standard tank, Особовый tank, a concept that combined the heavy armor and firepower of heavy tanks with the size and weight of medium tanks. In the meantime, the Kartsev Bureau at Uralvagon had continued to plan the evolution of the T-62. The team investigated using a new type of suspension with smaller road wheels and return rollers, and also began work on an autoloader for either a 115 mm or 125 mm gun. These features along with other design innovations were incorporated into the Bayekt 166 and Bayekt 167 tanks. On August 15, 1967, the Uralvagon plant was informed that it would transition from the manufacture of the 16 T-62 tank to the T-64A tank in 1970. Two variants were envisioned, the basic T-64A with the troubled 5 TDF diesel engine, and a mobilization version using a normal diesel engine from the T-62, which was intended as a low-cost alternative in the event of war. Kartsev hoped to develop a rival to the troubled T-64A, but was firmly rebuffed by Moscow. The political chief of the defense industry, Dmitry Ustinov, continued to back the elegant and futuristic T-64A as the way of the future. In spite of Ustinov's continued preference for the Kharkov option, the Minister of Defense Industry, S.A. Zavarov, had been impressed by a demonstration of the Uralvagon autoloader, and on January 5, 1968, instructed Kartsev's bureau to continue working on a mobilization version of the T-64A tank with the bureau's own autoloader and the improved V45 diesel engine. This version, designated a Bayekt 172, comprised a T-64A hull and turret reconfigured for the new autoloader and cheaper power plant. Two examples were completed by the late summer of 1968. Comparative testing during 1969 uncovered a number of design flaws, but the results of trials had been sufficiently promising for Uralvagon to be authorized to build 20 prototypes. The delicate running gear of the T-64A remained a source of mechanical problems. The rivalry between factions in the industry and the army supporting Kharkiv and Nizhny Tagil continued unabated in the late 1960s. The preference of senior army commanders for the simpler and more reliable Uralvagon approach counterbalanced the influence of Ustinov and the Kremlin bureaucracy. In the midst of the controversy, Kartsov was transferred from Uralvagon to an Army Tank Research Institute and his place was taken by Vian Venediktov. On May 12, 1970, a state decree on standardizing the T-64A gave Uralvagon permission to develop a further elaboration of the Obyekt 172, which took it even further away from the T-64A configuration by permitting incorporation of the new suspension from the Obyekt 167. This version was designated Obyekt 172M, and a prototype was ready by the end of 1970. The first of the T-72 export variants was the T-72 model 1975, like this example from the Iraqi 3rd Saladin Armored Division, captured in 1991 by the U.S. Marine Corps and subsequently displayed at Quantico, Virginia. The most characteristic feature of this version is the use of a coincidence rangefinder with the optical port in the protrusion in front of the commander's cupola. Author. A similar battle was being waged in Leningrad over plans to convert the plant there to T-64A production. The alternative approach here was to go one better than Kharkiv and adopt a more powerful gas turbine engine, a decision that would prove every bit as problematic as the opposed Piston 5 TDF. In the event, by 1971 the Soviet tank industry had 3 new standard tanks on hand, the original T-64A, and 2 derivatives, ready for trials, Obyekt 172M, T-72, and Obyekt 219, T-80. A pre-production batch of 15 Obyekt 172MS was completed by the summer of 1972 and subjected to a grueling field trial in June to October 1972. Overall, the Army was very impressed by the durability and firepower of the Obyekt 172M. Ustinov continued to oppose production of the Uralvagon tank, but the Army continued to press for its manufacture due to lingering reliability issues with the T-64A and the immaturity of the new Obyekt 219, T-80. To settle the matter, the Kremlin ordered the creation of a special commission under the first Deputy Minister of Defense, Marshal I. Yakubovsky. By this stage a second pre-production batch of Obyekt 172MS had been completed, in which most of the problems found in the 1972 trials had been rectified, so the Commission recommended production. On August 7, 1973, Obyekt 172M was accepted for Army service as the T-72 standard tank. In 1975 it was named the T-72 Ural after its birthplace in the Ural mountain region. The initial production series of 30 vehicles was completed by the end of 1973, with 220 more completed in 1974. In April 1976 Defense Minister Marshal Andrei Grechko died and his place was taken by Ustinov, who had never favored the T-72 and referred to it as a step backwards in Soviet tank development. Since the production debates of 1970-72, his support had shifted from the troubled T-64 to a new champion, the gas turbine-powered T-80. Developed by a consortium of Leningrad concerns with powerful 9.53 meters, 31.3 feet, T-72M one-side U-18 political connections within the Kremlin. As a result, Ustinov put a cap on T-72 advances. The T-64 and T-80 would serve as the premier Soviet standard tanks with forward-deployed units facing NATO and Germany and would receive priority for technological innovations in fire control and advanced protection, while the T-72 would be used for second-line units in the Soviet Union as well as for export. The T-72 underwent continual evolution during production. The second production series, Obyekt 172M SB-1A, incorporated several modest changes and can be distinguished from tanks of the early production series by the shift of the Luna infrared searchlight from the left side to the right side of the gun. This version, sometimes called the T-72 Ural 1 model 1976, was in series production at Nizhny Tagil from 1975. A command tank version, the T-72K Ural K, Obyekt 172M SB-2, was next in the 3.59 meters, 11.8 feet 2.19 meters, 7.2 feet, T-72M1 front view, T-72M1 rear view, interior cross-section of the T-72 tank. 19 development cycle, and was similar to the T-72 model 1976 except for the added radio and navigation system. The original T-72 versions through 1977 used laminate armor and the glassy plate, but had a conventional monolithic cast steel turret. The laminate glassy plate comprised an initial layer of 80 mm high carbon steel armor, followed by 105 mm of GRP, glass reinforced plastic or stecloplastica, about a quarter of the density of the steel, and finally a 20 mm layer of high carbon steel. The contemporary T-64 variant, the T-64A, also used laminate glassy armor, but instead of the monolithic steel turret was fitted with a special armor turret which had a large cavity in the front that was filled with aluminum. The monolithic steel turret of the T-72 was about 2% better at resisting APST's attack, while the T-64A turret was about 10% better against shaped charge attack. However, firing tests discovered that the T-64A's apparent advantage was less than it seemed, because after a single hit the cavity tended to deform and lose its protective advantage. The next generation of special armor used a combination K4 corundum, or ceramic, layer in the turret. The original configuration developed by Nistali, the State Research Institute for Steel, used ceramic balls and an aluminum matrix. Although this went into production for the T-64A in 1975, it was difficult to manufacture and was soon replaced by a modified version using ultra-porcelain, ultra-farforoff, ceramic rods instead of balls, also sometimes called sandbar armor. The new turret special armor with ceramic rod filler was first used on an interim version of the T-72 series, the T-72 model 1978, a Bayekt 172M SB4, which entered 20. The T-72M1 was by no means equivalent to the best Soviet tanks of the early 1990s. The best T-72 variant at the time was the T-72B with contact reactive armor, pictured as an example of the T-72's export version, on display at the Nizhny Novgorod Yarmark Arms Show in September 1996. Iran subsequently bought this version, which had substantially better armor than the T-72M1 as well as better ammunition. Author, production in 1977. Besides the new turret armor, this version also incorporated a switch from an optical coincidence rangefinder to the TPD-K1 laser rangefinder. However, this version was relatively short-lived, being supplanted by the T-72A model 1979, a Bayekt 172M SB6, later a Bayekt 176, which represented the first substantial redesign of the T-72 family. This used the new ceramic rod turret filler and TPD-K1 sight, but also incorporated improved glassy laminate armor, new anti-shaped charge side skirts, and improved suspension with more travel for the road wheels, the improved 2A46 gun, and the Tucha smoke dispensers. This version was accepted for service in June 1979. The next production series, the T-72A model 1983, introduced anti-radiation cladding on the turret roof and several other changes, including the 16 mm glassy applique. Also a few years behind the Soviet standard, in 1977 Ustinov visited India, and a tentative agreement was signed to sell the latter country 5,000 T-72 tanks and help it set up a T-72 plant. In the end, this deal was not completed on schedule due to political changes in India, but it did accelerate the process of preparing the T-72 for the export market. The first T-72 export tank manufactured at Uralvagon was internally designated as a Bayekt 172M E for Exportny, or export. By the time the Indian deal was under discussion, the Soviet government was also encouraging Poland and Czechoslovakia to begin license production, and agreements were reached in 1978. Production of the T-72 model 1975 export tank began at the Bumer-Lebedy plant in Poland in July 1982 and at the Martin plant in Czechoslovakia in 1982. There were two versions of this tank built, The Abiyak 172ME with the standard Soviet PRKHP and FTP-100M nuclear/biological/chemical (NBC) protective suite intended primarily for Warsaw Pact armies, and the Abiyak 172ME1 with a modified protective system using hermetic sealing and a turboseparator intended primarily for export to Middle Eastern countries, including Libya, Algeria, Syria, and Iraq. 22 An Iraqi T-72M1 engaging targets on the Bismaya gunnery range outside Baghdad in October 2008. The reconstituted Iraqi army still uses the T-72M1 tank, though most are newly acquired, reconditioned tanks obtained from former Warsaw Pact countries. U.S. DoD, the second export version, the T-72M, Abiyak 172ME2, began development in 1978. With production for export clients beginning at Nizhny Tagil around 1980 and in Poland and Czechoslovakia by 1985. The T-72M was a hybrid of the Soviet T-72 and T-72A in terms of features. For example, it used the TPD-K1 laser rangefinder as found on the T-72A, but was still fitted with the monolithic steel turret. The initial production version, the Abiyak 172ME2, had the original 2A46 125mm gun without the thermal shield and still carried the basic ammunition load of 39 rounds for the main gun. This version was followed by the Abiyak 172M1E3, which added a thermal sleeve to the 125mm gun, increased ammunition stowage from 39 to 44 rounds, introduced the improved TNP-149-23 night sight in place of the earlier TNP-149, added the Tucha smoke grenade launchers to the front of the turret, and added the anti-heat side skirts. In parallel, the Abiyak 172M1E4 was built for export outside of the Warsaw Pact and was essentially similar to the E3 except that it was fitted with the same NBC protective suite as the export T-72, Abiyak 172ME1. The T-72M was finally cleared for the use of special armor in the turret in 1982. The resulting T-72M1 export tank was a close relation to the Soviet T-72A. This version had the improved turret front armor using ceramic rods and an upgraded glassy plate with 16mm steel applique. There were numerous other upgrades compared to the T-72M, including better shock absorbers and an improved driver's hatch. Production of the T-72M1 began in Poland and Czechoslovakia in 1986. Two basic versions were manufactured, the Abiyak 172M1E5 for the Warsaw Pact, and the Abiyak 172M1E6 for export outside Europe with the alternative NBC protective suite. The main client for the Abiyak 172M1E6 was India, which built the model locally under license as the T-72M1IA. These export variants are significant in the case of Iraq, since all Iraqi T-72s were export models, including the T-72, Abiyak 172ME1, T-72M, Abiyak 172M1E4, and T-72M1, Abiyak 172M1E6. Iraq purchased its first batch of 100 T-72-1s, Abiyak 172ME1, from the USSR in 1979-80. Following the outbreak of the war with Iran, the USSR restricted its sales to Iraq since it was also courting Iran. However, the USSR encouraged its Warsaw Pact allies to take its place. Thus, in 1982 23 T-72M1 specifications T-72M1, 2nd Armored Brigade, RFGC Medina Armored Division, Medina Ridge, Iraq, February 1991 General Crew, 3 overall length, 9.53 meters hull length, 6.86 meters width, 3.59 meters height to turret roof, 2.19 meters ground clearance, 0.49 meters track contact, 4.29 meters track width, 580 mm gunner's night vision TPN 149-23 driver's day/night vision, TNPO-168 and TVNE-4B, Active IR/Passive 2, Commander's Day/Night Vision, TNP-160 and TKN-3 Commander's Searchlight, OU-3 GKM with IR Filter Fire Protection Automatic Freon System, 9 detectors. Unit price $1,200,000, $1,800,000 with ammunition and spares, 1992 export, motive power engine, V46X 12-cylinder diesel, 780 horsepower, 575 kilowatts, at 2,000 RPM fuel capacity, internal plus external, 705 liters plus 495 integral, plus 400 liters in 2 fuel drums. Performance maximum road speed, 60 km per hour. Fording capacity, 1.2 meters without preparation, 5.0 meters with preparation. Slope handling capacity: 30 gradient, 25 side slope. Obstacle handling capacity: 0, 85 meters vertical, 2.9 meters. Trench power to weight ratio, 19.8 horsepower/T, 14 kilowatts/T. Ground pressure, 0.9 kilograms/cm2. Armament: main armament: 2A46M, D81 TM 125 mm smoothbore gun. Main gun rate of fire, 8 revolutions per minute. Autoloader, 2 revolutions per minute. Manual. Main gun stabilization: 2E28M electro-hydraulic, 2-axis. Main gun elevation, -6 to +14. Secondary armament: coaxial PKT 7.62 mm machine gun. Anti-aircraft defense, 12.7 mm NSVT Utes machine gun. Smoke dischargers: Type 902A2 CHA, 12 cover 300 square meters for 2 minutes. Crew self-defense: AK-47S assault rifle, 10 F1 grenades. Poland sold Iraq a batch of 250 T-72 MS, a Bayekt 172 M1E4, followed in later years by the improved T-72 M1, a Bayekt 172 M1E6. Iraq purchased a total of 1,038 T-72s of all types, mostly from Poland. In the late 1980s there were plans to begin T-72 M1 production at Taji in Iraq in cooperation with Bummer Labadi. The process was to begin in 1989 using knockdown kits from Poland, with the locally assembled tanks called Azad Babil, Lion of Babylon. There are conflicting accounts regarding how many, if any, were actually completed. Polish officials indicate that none were completed, even though a T-72M displayed at an Iraqi of Soviet tank design in the 1960s led to a host of standard tanks that were substantially smaller and lighter than their NATO counterparts. A combat-laden T-72M1 weighed 41.5 tons compared to 56.8 tons for the M1A1, thus being one-third lighter. One of the most immediate results of this was the amount of internal space for the crew. The T-72M1 is extremely cramped, especially in the driver's compartment, with conditions being only marginally better in the turret. The M1A1, while not as spacious as the previous M60A3 tank, was positively luxurious compared to the T-72 with ample space for the loader and the rest of the crew. While this may seem irrelevant to tank design, it reflects the relative inattention of Soviet designers to crew ergonomics and the impact of these features on combat performance. The T-72M1 was not well suited to prolonged combat operations in desert climates because the extremely restricted space within the vehicle led to overheating, crew fatigue and excessive crew stress. Although Operation Desert Storm was fought during the winter months, temperatures even during February were sometimes warm enough to negatively affect crew performance. Air conditioning in the T-72 was provided by a small, unshielded plastic fan. This might be adequate in Russian or European climes, but was of dubious value in the desert. Protection: modern main battle tanks have their best armor towards the front, with the usual design requirement being for them to provide optimum protection in the forward 25-26. In the M1A1 the crew is protected from the risk of ammunition fire by a hydraulically operated blast door that separates the ammunition stowage in the bustle from the crew compartment. The loader opens the door using a knee pedal, so as to keep his hands free while transferring ammunition to the gun breech. Author, 60-degree sector. This involves an inevitable design compromise, since it is impossible to provide equivalent protection in all directions while remaining within viable weight limits. As a result, in this text the focus is on frontal protection for these two tanks. The side and rear protection is inevitably significantly less. Most contemporary assessments of tank protection distinguish between protection against APST projectiles versus shaped charge, HEAT, warheads, since modern laminate armors offer different levels of defense against these two distinctly different threats. The level of protection is usually expressed as equivalent to a certain thickness of rolled homogeneous armor, RHA. It should be borne in mind that information on armor protection is still widely regarded as sensitive, so the data here cannot be regarded as definitive. The figures on T-72 protection are from official published Russian sources. In general, the T-72 and T-72M were designed to be able to resist and strike equivalent to the Soviet 115 mm tank gun firing a steel APST projectile. This was considered roughly equivalent to the NATO 105 mm gun of the time. The defense against heat was proof against a shaped charge roughly equivalent to the Soviet 9 M14 Malyuta, AT-3 Sagar, which was viewed as equivalent to NATO types such as TOW. Curiously enough, this was the same threat level for the original M1 Abrams tank. The T-72M1 was designed to be proof against the improved 105 mm threats of the early 1980s, such as the Israeli 105 mm M111 APSTs with a tungsten carbide penetrator, or its American equivalents such as the M735, M735A and M774. Data is also presented here for the T-72B1. This was not in Iraqi service, but the data provides an idea of improved protective levels for newer generations of Soviet tanks, intended to counter the newer generation of NATO 120 mm tank guns and improved anti-tank missiles such as TOW-2. There is no unclassified data on M1A1 protective levels from U.S. official sources. The data below for the M1A1 is based on Soviet estimates. No data has been released on the amount of additional protection offered by the M1A1 heavy armor upgrade, so the data here should be regarded as estimated. The T-72 had a greater tendency to lose its cap compared to earlier types such as the 27. This overhead view of one of the M1A1 prototypes at Aberdeen Proving Ground in the United States shows the distinctive rectangular blast panels on the rear of the turret roof that are designed to NTOA a fire or explosion should the tank's ammunition ignite. U.S. Army, Comparative Protective Levels, RHA, Hull vs. APSTs, Hull vs. Heat Turret vs. APSTs, Turret vs. Heat T-72 335 450 380 410 T-72M 335 450 380 410 T-72M1 400 490 380 490 T-72B1 530 900 520 950 M1A1 600 700 600 700 M1A1 Ha 600 700 800 1300. As is evident from the table, the protective level of the best Iraqi T-72, the T-72M1, was inadequate to provide protection against the 120 mm gun of the M1A1 at normal battle ranges. Conversely, the armor of both the M1A1 and M1A1 Ha could provide adequate frontal protection against the 125 mm gun of the T-72M1, especially when the gun employed the most commonly available tank ammunition, the 3U BM7 round with BM15 penetrator. Both tanks could defeat each other in side or rear engagements. The tanks differed significantly in internal layout, which affected survivability if penetrated. The T-72 had 22 of its 44 rounds of main gun ammunition in a two-tier carousel under the turret floor, which fed the autoloader. The rest was stowed in various locations around the fighting compartment. The location of so much ammunition in such a confined space was an invitation to catastrophe should the T-72 be penetrated. One of the more curious innovations on many Iraqi RGFC T-72s was a missile jammer, the cylindrical device on the far right in this photograph. This device emitted an infrared beam that was intended to confuse the fire control of standard NATO anti-tank missiles such as the Milan and TOW, as used by the coalition in the 1991 war. The U.S. modified the TOW guidance S. More curious innovations on many Iraqi RGFC T-72s was a missile jammer, the cylindrical device on the far right in this photograph. This device emitted an infrared beam that was intended to confuse the fire control of standard NATO anti-tank missiles such as the Milan and TOW, as used by the coalition in the 1991 war. The U.S. modified the TOW guidance system before the war to counter this. Author, 28 T-55, due to the increased volume of propellant carried inside the fighting compartment. A fully loaded T-72 carried double the propellant of the T-55 to 440 kg compared to 220 kg. The T-62 was in between at around 310 kg. The M1A1 had 34 of its 40 rounds of main gun ammunition in a protected bustle in the rear turret overhang and the remainder in protected ready racks inside the turret. The aim of this configuration was to minimize the risk of the ammunition being struck by hypersonic debris if the turret was penetrated, and if the ammunition racks were ignited, to vent the blast upwards through special blast panels in the roof rather than forward into the fighting compartment. This was intended to prevent catastrophic destruction of the tank and to give the crew more time to escape. The combination of better armor and better ammunition protection gave the M1A1 a clear protection advantage over the T-72M1. Firepower T-72. The T-72 was armed with the 125mm D81TM 2A46 gun, an improved version of the D81T 2A26 125mm gun that went into service on the T-64A in 1968. This was a conventional smoothbore gun with a life expectancy of 600 rounds of heat ammunition or 150 rounds of APST, although export customers complained that the actual useful life was closer to 100 rounds of APST. Barrel life was a significant issue for Iraqi tanks as a large proportion of the inventory had been employed during the Iran-Iraq War and the Iraqi army was not especially diligent about keeping its equipment in prime condition. Accuracy suffered due to tube erosion. The usual two types of anti-tank ammunition were available, APSTs and heat. The 125mm ammunition was of the split type, with a projectile and a semi-consumable propellant case and a steel stub casing at the base. At least 4 types of APST ammunition were available for export at this time, most of them already 2 decades old. Details of Iraqi ammunition stocks are not available, however, even though Iraq was manufacturing the 3VBM-7 ammunition in the late 1980s. The U.S. Army regularly encountered the old 3VBM-3 ordnance during the 1991 fighting. By way of comparison, the best Soviet APSTs around 1990 was the 3VBM-13 Vaunt, which had a 3BM-32 depleted uranium penetrator with penetration capability of 560 mm at 2 km, about double the performance of the 3VBM-3 used by the Iraqis. One should note that Soviet ammunition designations are confusing since there were 3 GRAU, Main Missile and Artillery Directorate, designations, the overall ammunition round, the projectile, including the sabot pedals and other housing, and the penetrator arrow itself. The table below lists all 3. In general, the APST performance of the Soviet 125mm gun was inferior to that of the US 120mm gun. 2 types of heat ammunition were available for export prior to Operation Desert Storm, 3VBK-7 and 3VBK-10. These employed conventional finned projectiles with copper liners for the shaped charge warhead. Penetration capability for the 3BK-14M, 3VBK-10, was about 500 mm. Neither type was capable of penetrating the M1A1 frontally. 29 Soviet 125mm APST ammunition round projectile penetrator. Date of introduction: initial velocity, meter per second, weight, kg, penetration, RHA at 2000 meters, 0 degrees, 3 VBM 3 3BM 10 3BM 9 1962 1803.6 293 VBM 6 3BM 13 3BM 12 1968 1803.6 315 3 VBM 7 3BM 16 3BM 15 1972 1783 9 343 VBM 8 3BM 18 3BM 17 1972 1783.9 330 The best Iraqi 125mm ammunition in 1991 was the 3 VBM 7 Abrams round, which used the BM-15 penetrator, seen here with an encapsulated tungsten carbine slug. The associated sabot pedals can be seen to the left. Author: the only automatic data input was for vehicle movement, and the T-72M1 fire control system did not incorporate corrections for crosswind data. Although the earliest version of the T-72 in Iraqi service was the T-72 model 1975, which was still fitted with the TPD-249 coincidence rangefinder instead of the laser rangefinder found on the later T-72M and T-72M1. This version can be most easily distinguished by the right-side optical port for the rangefinder that is located in front of the commander's cupola. Optical rangefinders date back to the late 1940s and are not as precise or as simple to use as laser rangefinders. Author: the 125mm gun was fed by a mechanical autoloader from the rotating ammunition carousel under the turret basket. The carousel contained an assortment of 22 projectiles and 22 ZH-40 propellant cases, stowed horizontally with the projectiles forming the bottom layer and the propellant cases the top layer. The additional rounds were stored in the hull around the turret, 4 projectiles and propellant cases in pockets in the right front fuel cells, 2 projectiles and ZH-40 cases behind the commander's seat, 2 projectiles and 1 ZH-40 case immediately behind the gunner, 3 projectiles on racks on the left rear hull side, 6 projectiles on the rear firewall, and 8 ZH-40 propellant cases in cavities in the rear fuel tank, on the floor behind the ammunition carousel. The only ammunition stowage above the turret line comprised 5 propellant charges near the gunner's and commander stations. The gunner sat on the left-hand side and the commander on the right-hand side of the gun. In the T-72M1 the gunner sights comprised a TPN-149-23 active infrared night sight on the left and the primary TPD-K1 day sight with integral laser rangefinder immediately in front of him. The TPD-K1 offered 8 power while the night sight offered 5 power magnification. Turret traverse was controlled using a S. Would meanwhile aim the main TPD-K1 sight at the target and fire the laser rangefinder using a finger control. The range was displayed in the sight, and had to be manually entered into the tank's mechanical ballistic computer. The computer also required manual input of ballistic and meteorological corrections calculated from data available to the gunner before the engagement, degree of barrel wear, charge temperature, barometric pressure and ambient temperature. T-72M1 gunsight view T-72 gunner sight, clear conditions T-72 gunner sight, foggy/dusty conditions. The T-72M1 gunner's reticle was considerably more cluttered than the comparable M1A1 gunner sight, since it was a generation older in configuration and relied on more extensive manual inputs from the gunner. The T-72M1 had 2 reticles, the primary sight for the TPD-K1 day sight and laser rangefinder as seen, and the TPN-149-23 active infrared night sight. The gunner began by inputting the ammunition type which switched the sight reticle to the proper type, in this case, APSTS, indicated by Cyrillic letters that transliterate as BR on the lower right side of the vertical gradation. The Cyrillic letters that transliterate as POL indicate machine gun. With this data incorporated, the gunner then placed the red laser aiming circle over the target, using the center one for the main gun or the one on the right of the range scale for the coaxial machine gun. After firing the laser rangefinder at the target, the gunner read the digital result off the reticle and entered it into the system. The reading appeared on the semicircular dial at the top of the reticle, with the top gradations for the coaxial machine gun and the primary gradations at the bottom of the circle for the main gun. 22 indicates a range to target of 2,200 meters. If firing on a moving target, the gunner had to place the red laser circle over the target for a few seconds while tracking the target, which entered data about the amount of lead required. Once the range was entered, the gunner then had to place the target above the main aiming mark, the inverted V at the center of the main set of gradations, as shown here. This process was so complex, especially under the stress of combat, that Iraqi tankers were often instructed to battle sight their guns, which meant entering a default set of range and ammunition data so that the gunner had only to place the aiming mark on target and fire. The default solution was usually APST's ammunition at a range of 1,800 meters. This may have been a major reason for the poor Iraqi shooting during Operation Desert Storm, since U.S. tanks typically began engaging from ranges beyond 1,800 meters, and Soviet-made APST's ammunition was much more prone to dropping at extended ranges than American APST's due to the larger fins. The main reason for the poor Iraqi gunnery during Operation Desert Storm is better illustrated by the second sight image, which depicts an engagement such as that at Medina Ridge. The overcast weather, rain, dust clouds and other conditions essentially made the U.S. Army M1A1 tanks invisible to the Iraqi gunners through their sights. The only aiming points were occasional flashes from the Abrams 120mm main guns. Even if the Iraqi gunner was well trained and attempted to use the laser rangefinder in the prescribed manner, the rangefinder was apt to provide false returns due to the rain and fog. This left the Iraqi gunners to try to aim at the flashes without proper range data, and if their guns were battle-sighted at the usual 1,800 meters, the APST's round would fall considerably short. A autoloader theoretically allowed a maximum rate of fire of 8 rounds per minute. In practice, the rate was likely to be more limited due to the time required to carry out the fire control sequence. With limited training, Iraqi T-72 crews would often battle-sight the gun to a predetermined range, usually 1,800 meters, and leave these settings in place. The night vision system for the gunner was active infrared using the Luna 2 AGM turret searchlight and had an effective nighttime range of 800 meters. The tank commander's TKN-3 daysight/nightsight also had an infrared channel, and the commander was provided with a small U3 GK searchlight for independent illumination, which provided coverage to about 400 meters. The 125mm gun in the T-72M1 used a 2E28M electro-hydraulic stabilizer. This fire control system performed similarly to those used in the early 1970s generation of Western tanks, such as the M60A1 Rise, Leopard 1A3, Chieftain Mk5 or AMX-30. The system was poorly suited to firing on the move due to the complexities of manual data input and the inherent limitations of the gun stabilization system. Firing on the move in the T-72 was only accurate on level ground, at moderate speeds, up to 25 km per hour, and against a target with small lead angles. The gunner's station was not well designed for firing on the move, with little thought given to providing large brow pads or a chest rest to permit stability during high-mobility action. Because of these limitations and poor crew training, Iraqi T-72 tanks normally fired from a stationary position. In contrast to Iraqi tank ammunition, which relied on steel penetrators or steel with a tungsten carbide insert, the M829A1 used a solid depleted uranium rod. Depleted 32, a remarkable photograph of an APST projectile in flight, with the aluminum sabot petals peeling away from the long rod penetrator. The sabot holds the small diameter penetrator centered in the gun tube during firing, and is the source of the U.S. Army's nickname for this type of ammunition, Super Sabot. M1A1. The M1A1 Abrams was armed with the M256 120mm gun, a license-built derivative of the German Rheinmetall gun used in the Leopard 2 tank. By the time of Operation Desert Storm, the preferred ammunition for tank fighting was the M829A1 APST's round, popularly called the Silver Bullet for its outstanding anti-armor penetration. Alliant techs due to its extreme density as well as its unique properties. i.e. when impacting armor at high velocities. Du has a density of 18.6 grams/kg compared to only 7.8 grams/kg for steel. Heavy metal penetrators with comparable densities to Du, such as the traditional favorite, tungsten carbide, exhibit less armor penetration than Du due to differences in effect under the extreme pressure of impact. When a tungsten carbide penetrator tip hits armor plate, it deforms into a broad mushroom shape, much like other metals such as lead, making a wider crater and expending a relatively high amount of energy. In contrast, Du penetrators 33 this cutaway of a 120 mm M829 APSTS projectile shows the basic components. Due to the use of a single-piece round, the penetrator could be longer than those used in Soviet two-piece 125 mm ammunition. Olin Ordnance, 34. The effect of APSTS ammunition can be seen on this burnt-out Iraqi T-72 model 1975. The impact point was circled with a chalk mark by a U.S. evaluation team inspecting tank wrecks after the fighting. U.S. DoD, undergo adiabatic shear. During penetration, small fragments flake off the tip, leaving a chisel tip which creates a narrow crater, making better use of the energy. The second reason for preferring Du over tungsten carbide was its pyrophoric effects. The high velocity impact of Du against steel creates small incandescent particles, creating a secondary incendiary effect after penetration which increases internal damage to the enemy tank. Although official figures are lacking, published estimates of M829A1 penetration capabilities are 670 mm at point-blank range, 620 mm at 1,000 meters, 570 mm at 2,000 meters and 460 mm at 4,000 meters. In other words, the M829A1 round was capable of penetrating the T-72M1 at normal battle ranges from any angle. The much superior penetration capabilities of the M829A1 compared to Soviet 125 mm ammunition were due to a variety of factors. The NATO 120 mm gun offered higher chamber pressures than the Soviet 125 mm gun, 5,650 bar versus 4,600 bar, which provides some indication of the amount of energy exerted on the projectile. The Soviet use of split ammunition also limited the length of the penetrator dart. Although the Soviet 125 mm gun had a higher muzzle velocity, the short penetrator length required wider fins that led to a more rapid loss of speed at longer ranges compared to the long rod penetrator of the U.S. projectile. The performance of the M829 and M829A1 rounds during Operation Desert Storm surprised the Abrams crews. During peacetime firing, such rounds were not used. Instead, training rounds with ballistic safety cones fitted to stop the rounds going too far were used. This in turn degraded the training rounds' ballistic performance and required a different ballistic solution in the tank's fire control due to the high arch of their trajectory. Captain Mark Jurgis commented about experience with combat loads during the fighting. M1A1 gunsight view. M1A1 gunner sight, daylight channel. M1A1 gunner sight, thermal imaging channel. The M1A1 gunner's primary sight, GPS, had both an optical daylight channel and a thermal imaging channel which could be used day and night. Like the T-72M1 gunner, the Abrams gunner began the process by manually entering the ammunition type. The reticle in the center of the sight consisted of an aiming box 1 milliradian, in size, equivalent to a target 1 yard wide at 1,000 yards. The aiming mark totals 20 mil across. The gunner squeezed the laser trigger, which provided a range in the green digital display below, in this case, 2,000 meters. Unlike the T-72M1, this data was automatically entered into the ballistic computer and the system made the appropriate gun elevation corrections. The small rectangle to the upper left of the laser range readout is a ready-to-fire symbol. An F symbol appeared on the opposite side in the event of a system malfunction. The line above the laser readout indicated multiple laser returns, which would be unlikely in this case and more commonly arose when attempting to determine range through trees or other obstructions. One of the Abrams' main advantages during much of the Desert Storm fighting was the thermal imaging channel in the GPS, which sensed temperature differences between the objects being viewed. In this case the system is set at white hit, meaning that warmer objects appear as bright spots and cooler objects appear darker, even in cases where light fog or rain might obscure the targets, as occurred at Medina Ridge. The thermal sight permitted the gunner to locate targets. The system did have its limitations, particularly at ranges much beyond 2,000 meters, as the targets then appeared as little more than glowing blobs, making it very difficult for the gunner to differentiate between friend and foe, or between tanks and BMPs. 35 at ranges out to 3,600, or even 4,000, there was no observable ballistic solution to the round, it was flat. The kick from the service ammo was also a surprise, and more violent than the not-so-gentle rock we were used to with training ammo. The tanks carried two types of sabot, a load of M829 and 7 rounds of M829A1, which we called Super Sabot. The plan was to use up the M829 on targets getting to the decisive showdown with the Republican Guards, and then shift to the Super Sabot because we thought the greater armor on the T-72 minutes 1 second would need the better round to penetrate. Not quite. We fired only 1 or 2 Super Sabots in my entire company during the fighting. The M1A1 used an integrated gun-slash-turret stabilization system with line-of-sight stabilization and elevation and gun-slash-turret stabilization and azimuth with hydraulic power for the gun and the turret. The gunner's station was designed from the outset to permit fire-on-the-move operations. For example, the gunner was provided with a large brow pad to keep his face comfortably away from the sight aperture and other obstacles. The gunner was also provided with a ch/turret stabilization system with line-of-sight stabilization and elevation and gun/turret stabilization and azimuth with hydraulic power for the gun and the turret. The gunner's station was designed from the outset to permit fire-on-the-move operations. For example, the gunner was provided with a large brow pad to keep his face comfortably away from the sight aperture and other obstacles. The gunner was also provided with a chest rest so that during jarring tank motion he could wedge himself into a firm operating position between the seatback and fire controls. The fire control system was designed to minimize the need for numerous data inputs, which instead were handled automatically. The laser rangefinder was integrated into the gunner's primary sight. The fire control system utilized a digital ballistic computer designed to be operated with minimal training, using automatic data inputs to improve overall gun accuracy with minimum attention from the gunner. It would automatically input data from wind and cant sensors, as well as data on tracking rates for lead corrections based on the turret traverse. The gunner would manually enter other data, such as air temperature, ammunition temperature, barometric pressure and tube wear, but this 36 fire control innovations gave the M1A1 Abrams still greater accuracy. The device at the end of the gun barrel is the muzzle reference system, an optical sensor that links to the fire control computer to indicate the amount of barrel warp induced by thermal heating and other factors. The data is then automatically entered into the digital ballistic computer to determine the necessary aiming corrections. GDLS could be done prior to the engagement to minimize the need for attention during combat. The gunner's primary sight was configured for both a 3-power wide field of view for surveillance and target acquisition, and a 10-power narrow field of view for aiming. The most substantial difference between the fire control systems for the M1A1 Abrams and the T-72M1 was the provision in the M1A1 of an integrated thermal imaging subsystem, TIS, 2 generations more advanced than the T-72M1's active infrared system. Active infrared systems required infrared searchlights for nighttime illumination, which made any tank using such a system glaringly evident to enemy tanks. Most major NATO armies shifted from active infrared to image intensification night vision systems in the late 1970s. Image intensification sights were passive, without the need for dangerous searchlights. They relied on ambient moonlight or other sources for illumination. These electro-optical sights collected the small amounts of light available even with partial moonlight, and amplified them sufficiently for the gunner to be able to acquire and engage targets. Their main disadvantage was that they 37 above. The thermal imaging system provided the M1A1 Abrams with a critical technological edge during Desert Storm. Manufactured by Hughes Aircraft Company, now part of Raytheon, these sights were quite expensive, accounting for about 10% of the cost of the entire tank. Hughes, left, the M1A1 gunner's primary sight, GPS, contains a thermal imaging system, and an optical extension is visible at the top of this picture which allows the commander to see the same image. Note that the commander, to the right, has his own hand control which allows him to slew the turret in the direction of the target. GDLS M1A1 Abrams Key 1. Loader's Seat 2, Tank Radio 3. Machine Gun Ammunition Compartment 4. Loader's M240 Machine Gun 5. Coaxial Machine Gun Ammunition Stowage 6. M256 120mm Gun Breech 7. Commander's M2 Heavy Machine Gun. 38-24538. Commander Sight 9. Gunner's Auxiliary, Telescopic, Sight 10. Gunner's Primary Sight 11. Gunner's Controls 12. Fire Control Computer Panel 13. Gunner's Seat, Backrest Folded Down, 14. Commander's Handles 15. Commander's Control Panel US 120mm Ammunition. The M829A1 120mm APST T, Armor Piercing, Fin Stabilized, Discarding Sabot, with Tracer, was the premier U.S. tank fighting ammunition of Operation Desert Storm, variously nicknamed the Silver Bullet or Super Sabot. In tankers' parlance, this type of ammunition is nicknamed sabot, a contraction for the otherwise excessive fold designation of the ammunition. Sabot, from the French word for a wooden shoe, refers to the light metal jacket around the penetrator dart that keeps it in place in the gun tube during the firing process and which peels away after the round leaves the gun tube. The M829A1 used a long rod penetrator with a high length/diameter ratio, meaning that the dart was especially long compared to the diameter of the rod. The penetrator itself was machined out of depleted uranium, which offers both high mass and excellent penetrating qualities. The M830 120mm Heat MPT, High Explosive Anti-Tank Multipurpose with Tracer, was the other combat round regularly used by U.S. tanks in Operation Desert Storm. By this time, the APST was the preferred tank fighting round, but it was not ideal for use against light armored vehicles since it was so powerful it tended to pass completely through the enemy vehicle. Heat ammunition was the preferred type when dealing with light armored vehicles since the shaped charge, high explosive warhead could easily penetrate any armored vehicle, and the behind armor effect of the warhead was very substantial, causing a tremendous amount of internal damage to the enemy vehicle. The heat round was considered a multi-purpose round in the U.S. Army since at the time, a dedicated high-explosive fragmentation, HE-frag, round was not on hand for the 120mm gun. The T-72 had both a heat and an HE-frag round. HE-frag ammunition is traditionally used against soft, that is non-armored targets such as trucks, emplacements and buildings. Lacking a dedicated HE-frag round, the heat round was used in its place when engaging these targets. 11-1456. Nation, at least 1/4 moonlight, and this might not be available on totally moonless or cloudy nights. The next generation of sights, thermal imaging or FLIR, forward-looking infrared, sights, got around the limitations of the image intensification sights by sensing minute differences in reflected or ambient infrared energy. Tanks moving at night have a very distinctive infrared signature since their engines give off thermal energy, as do their wheels and tracks. Even stationary tanks have a distinct signature since they collect solar heat during the day, which disperses at night. The thermal sights have a secondary function in daytime, since they have some capability to peer through atmospheric phenomena such as smoke, mist, and fog that would be opaque to normal human vision. Thermal sights were first used on the U.S. Army's M60A3, TTS, tanks. The TIS on the M1A1 was better integrated than the T-72M1 gunner's night sight, which used a reticle separate from the gunner's normal fire controls. The M1A1 had an auxiliary sight, a conventional telescopic sight, for use in the event of failure of the primary equipment. The T-72M1 lacked a spare sight. In terms of firepower, the M1A1 outclassed the T-72M1 in all respects. It had better ammunition, better penetration, better performance at longer ranges, more sophisticated fire controls, better fire-on-the-move capability, and better crew ergonomics. But regardless of the technical details, the bottom line was that the 125mm gun and the ammunition available to the Iraqis could not frontally penetrate the M1A1 tank, while the M1A1's 120mm gun could penetrate the frontal armor of the T-72M1 at typical combat ranges. Mobility: the M1A1 Abrams was powered by an AFCO-Lycoming AGT 1500 gas turbine engine. This offered 1,500 horsepower or about 23 horsepower/T. Turbines provide more power for a lighter weight than did comparable diesels of the time, and offered superior sustained high-speed travel. Their main drawback was higher fuel consumption. During typical peacetime training exercises, U.S. tankers found that the M1A1 Abrams could operate for about a day on a single load of fuel compared to about 3 days for the earlier M60A3 tank. The M1A1 had a notional road range of about 290 miles. Ideal fuel consumption was 1.8 gallons per mile. The Abrams' actual range was quite variable, and usually lower, because turbine engines consume more fuel at idle than comparable diesel tank engines. Modern tanks do not shut off their engines when static, since it is necessary to keep the batteries charged to operate various electrical systems, including the radio and fire control system. The M1A1 had an hourly fuel consumption of 10.8 gallons at idle, 44.6 gallons on the road, and 56.6 gallons cross-country. The main solution to the Abrams fuel consumption problem was to provide adequate logistical support. An Abrams tank battalion had 16 HEM tanker trucks, each carrying 2,500 gallons of fuel. The T-72M1 was powered by a V46-6 diesel engine producing 780 horsepower. This gave the T-72M1 a power-to-weight ratio of about 19.8 horsepower/T and a maximum road speed of about 37 miles per hour, somewhat less than the M1A1. Internal fuel capacity was 1,000 liters, 264 gallons, and a further 400 liters were typically carried in 2 external drums. The T-72 had an optimal fuel consumption of 1 gallon per mile, so even though it only carried about half the internal fuel of the M1A1, its average road range was about the same. The M1A1 had better mobility than the T-72M1 in terms of actual power per ton, as well as better ergonomic design of the crew stations. However, the T-72M1 offered better fuel economy. The thermal sight image differs from conventional optical images in that warmer areas show up with greater intensity than cooler areas. This image of an M1 tank in motion shows the wheels and tracks as relatively hot due to friction. The gun barrel and engine deck are also more visible. U.S. Army, 41. The combatants: the most significant difference between the crews of the M1A1 Abrams and the T-72M1 Ural was the lack of a loader in the T-72M1, leaving it with a crew of 3 versus 4 in the Abrams. Otherwise, crew functions were very similar. There has been long-standing controversy over the desirability of autoloaders versus human loaders. The U.S. Army has generally favored human loaders for 2 reasons. Firstly, there is some advantage of a human loader over an autoloader in the first critical moments of a tank battle, since a well-trained crew can get off the first 3 rounds in around 15 seconds compared to 2 rounds or fewer from the T-72 autoloader. Secondly, U.S. tankers feel that additional crewmen are vital in day-to-day combat conditions due to the enormous amount of work required for maintaining and resupplying the tank, as well as providing security when at rest. In the Soviet view, using an autoloader saved a considerable amount of internal volume in the design, permitting a smaller turret and a smaller, lighter tank. Also, an autoloader permits a faster sustained rate of fire, about 8 rounds per minute in the T-72M1 compared to about 4 rounds per minute for the M1A1 Abrams. M1A1 tank crew. The M1A1 had a crew of 4, tank commander, TC, gunner, loader, and driver. All were stationed in the turret except for the driver, who was positioned in the center of the front hull. In the turret the loader was on the left and the gunner and TC were on the right. The tank commander was positioned behind the gunner and was responsible for leading the tank in combat. In a 4-tank platoon, the leader was a second lieutenant 4201. The platoon sergeant was usually a sergeant first class, E7, or staff sergeant, E6. The 2 wingman tanks would also be commanded by sergeants. The TC was stationed below a rotating cupola and hatch that provided all-round direct vision, when buttoned up, by means of periscopes. The TC was also provided with an optical adjunct from the gunner's primary C.